Hello everyone. Today I want to talk about the components of crane system and how to design a crane girder beam, bracket and column. We have a general layout of a crane. There is crane bridge, end carriage and the wheels here. We have hook point and there is crane girder or crane runway girder, bracket or corbel and the column. And drawings here same details, crane bridge, crab, crane girder, and carriage with these details, that is wheel sitting on a rail and rail sitting on the girder. Remember, when we say crane design, we generally design this beam, bracket or corbel and the column, and we don't mind about design of this crane bridge, crab and this hook point. That's already designed and manufactured by manufacturer. When we say design, it is mainly to transfer the vertical loads. When we have vertical load transformation, depending on the load value, we have different types of strengthening for the column. If the load is not big, we can use the existing column or the normal column with the same section from the top to bottom and rail here to transfer the load from a small extension to the column, and we need to check this beam, bracket and column. But if the load is big and the column is not able to take that one, we need to have some element straight under the load, crane load or rail load, to take that load to the ground, and also we need to stitch this new one to the column to strengthen the system. Also, we may have, if we have very big load, we may have just different sections for the column on top and bottom of the rail. So, but bigger section under the rail to take this big load and transfer it to the ground. And we may have similar arrangement for heavy loads, just vertical element under the crane here, and using a stitching to the column with some rigid frame to take the load and increase the capacity of the load to transfer the vertical and horizontal load, that we talk about that later. And just always remember, we should have free rotation at the support point of the girder beam. Free rotation at the support of the crane runway girder is important to avoid bending and torsional moments in the column. It is very critical, and always remember that these beams, these girder beams, are just simply sitting on these points and they are not fixed at those points. Here are typical section for girder beams. Rail can sit directly on the beam or girder, or it is sometimes, if we need a wider space, we can have some PFC sitting on top of the girder and rail sitting on top of PFC, or sometimes it can be combination of these two. We can just extend the top flange by adding some angles to edges of the girder top flange, and the rail sitting on top of the section, combined section for flange. And these are the very common rail fastening. It can be welded to top of the flange or just any of these combination, or it should be fully rigid by these clamps, or should be partially restrained by these clamps to the flange, top flange, and also should be just some partially restrained by adding some more details, some neoprene plastic under that, and just giving some freedom for the rail to move on that. And also it can be clamped or just hooked on top flange. This is front view and this is plan view. It could be just hooked on either side, one here, one the other side, and this is top view of the girder beam. This is general rail fastening on top flange of the girder beam. And just one more factor we need to just consider when we're going to design the crane is we will talk that about we always have some transverse load from the crane, inertia and crabbing forces coming to this top flange. In this load can just cause some cracking or just damage to the web of the girder. To avoid those things, we have to support this girder beam laterally to the column. It can be just adding some cleats like this, or the best option always to just connecting top flange to the column. That is the best option to avoid any damage to the web of this girder. So in this case here, we just make sure that we don't have any problem due to this transfer load to the web of the girder. But we still have just some more consideration, more load combinations and effect that we talk later. This is the general crane runway girder and the structure. This is front view. We have crane girder, rail on top of that, and the column. And this is bracket. In steel structures, we say bracket, but in concrete column, this can be just like corbel. And we need to have strut and tie model to design this one. But if it's steel, just depending on this depth of the corbel, it can be just bending design or shear design or combined action. And this is the side views. You see that here it is just connected from the middle. That is very dangerous. But if we have top flange connected to the column, it is very safe to taking the lateral loads from crane and crane bridge to this web. Let's talk about design procedure. Here, same arrangement. We have crane bridge, crab, hook point, end carriage on both ends, wheels. Normally we use 2 wheels in specified centers. And we have different length between these girders, that is LC here, AW, that is just length of this end carriage or the wheel center, and also we have L for supports for the crane girder. It should be just corbels, that is, it should be just supports on the column, and remember it is simply supported on those points. It's not fixed. So we have this length LC, L, AH. AH is the center to center of the lifting load to this rail. And just if we talk later, whenever it is close to this center, it has more effects, more reaction on this area. We have classification of cranes based on the load values and how big is compared to the safe working load or the capacity of the crane. If we have Q1 to Q4, Q1 is considered as light, Q2 moderate, Q3 heavy, and Q4 is very heavy. Q1 is it is far from the safe working load, from the capacity, and it is just normally very rarely used and normally light loads, and very heavy load is just the crane is normally loaded close to the working load, working capacity, and it is just frequently used. First step in calculations is calculating the maximum vertical loads. For load calculations, we have different items. We come back again to that slide. We have lifting load here, the bridge, crab, end carriage, and rail load, and rail self-weight, and this beam self-weight. So we consider all these things in this arrangement. First one is the weight of the trolley. It is carriage plus lifted load. We say RH. The weight of the crane bridge. We say RS. And also the self-weight of the crane girder and rails. That's called RG here. Just note, the load to the crane girder will be maximum when trolley wheels are close to the girder. We talk about these things. If this crane is very close to that area, it means that it has big effect on that area. If it is in the middle, it has the biggest effect on the bridge, and this load will be transferred equally on both ends. But if it is just close to any end, it has the maximum support reaction on this point that is going to be transferred by two wheels on the girder beam. So we have these vertical load cases and combination. If the crane is stationary, if it is just lifting the load, we have F gamma F times RH plus gamma F times RS. But if the crane is lifting the load and moving, it should be 25% higher. That is 125 gamma F RH plus 125 gamma F RS. F is the impact factor from British Code 2573-1. Gamma F is the partial factor for vertical crane loads from same code, from British Code 5950-1. And RH and RS are the loads from crane and hook and crane hook and the bridge. That's called before. If we have a warehouse or workshop, the F is 1.3, that is applicable for RH. Here you said that crane stationary. Lifting load is 1.3 gamma F RH plus same, no increasing in gamma F RS. And if the crane is moving, it is staying same, 1.25 gamma F RH plus 125 gamma F RS. But for conservative design, we assume that this 1.3 factor is applicable for RH and RS and covering all these things. So for conservative design, we assume that is 1.3 gamma FR or 1.3 gamma FRH, 1.3 gamma FRS in total for vertical load. R is the RH plus RS here. R is this load we had. 1.3 gamma FRH, 1.3 gamma FRS. So the maximum unfactored load, point load per wheel, should be half of this one. 1.3 times half RS over 2 RH, LH minus AH on LS. That is just simple calculation for this equation here. It is just reaction based on the distance between AH and LC. And if AH is close to 0, we have the biggest reaction here. But anyway, it is just per each wheel. Second step is horizontal loads. For horizontal loads, we have two types in general. One is inertia forces produced by the motion drives of brakes. Motion drives or brakes, that we call it surge load. And the second one are skew loads or traveling, referred to as crabbing force. Here in shapes, the first one is surge loads, longitudinal and transverse, and the second one is crabbing force. For transverse surge load, it is 10% of the combined weight of the crab and the lifted load. But for longitudinal load, surge load is 50% of the vertical reaction. It is from the weight of the crab, crane bridge, and lifted load. Here we have longitudinal load and transverse load, that is WH1 and WH2. And for crabbing force, we don't take in account for Q1 and Q2, but if it is Q3 and Q4 classification, we need to have these loads. And for calculation of this one, we need to refer to 5950 British code. But anyway, for horizontal loads, always we need to take WH1, WH2 as inertial loads for brakes and movement, and crabbing force for just Q3 and Q4. And one more important thing, that we never combine horizontal loads in one combination. It's coming in next slide. So for load combinations for this one, we have LC1 1.4 DL plus 1.6 WV, 1.4 DL plus 1.6 WH1 that we had as surge or just inertial loads, or WH2 or crabbing load. And same for load combination 3, 1.4 DL plus 1.4 WV plus 1.4 WH1, WH2 or FR. It is just or. We never combine horizontal load in one combination. So next is design checks for girder beam. Girder or just the runway girder beam or gantry. For that one, we have major axis bending. Here we have, if it is section, let's say if this is the section, we have major and minor effect, minor direction. For major, we have bending effect, major axis bending, and also we have lateral torsional buckling due to just lateral restraint of the flanges. And we have horizontal moment capacity that we will talk later, that is just taken by top flange. And also we will have combined action of vertical and horizontal moments. We will have web shear at supports, that is very critical for web check. And also we have local compression under wheels for web, and also web bearing and buckling under the wheel deflection. So for the girder, we have 3 checks for web, that is shear, local compression, and web bearing. We have horizontal bending for top flange, and also major bending for whole section. We have major bending, lateral torsional, and combined action of bendings. These are all we need to have to check for girder. And remember, after this, we need to check for bracket and also the column. So for major axis bending, let's say that we have supports here for L, that was the distance between supports on the columns here, and this rail is moving along this one. So let's say we have mx design bending moment from these loads and lifting load on this girder, And if we're going to just check for plastic section, it should be PY/SY. PY is yield strength, and SX is in major action is just the section modulus. And you can check for elastic design as well. In that case, it should be just 1.2 PY/ZX. That is just elastic section modulus, and PY is yield strength. It is easy. Just you don't need to check manually. If you have this design, normally it is very easy to check from the tables. If it is just hot rolled section, normal section, you can check from the comparison of the applied bending moment from combined action, and also what is the bending capacity of the section in the tables. And here note, we have for section classification of compound, if we have just compound action, and let's say if it is not just I, and if we have some flange on top of that, or just any addition to this section like additional flanges, we can just do the same calculations and refer to 5950 for bending check anyway. But the rules are the same. We have the section, we can calculate area, we can calculate section modulus, and after all we can calculate compare the applied bending moment in major axis with the section capacity. And one more important thing for major action, if we have higher shear on the girder, remember always we need to reduce the section capacity in bending. Just for this one, just you need to refer to 5950-1 section 4253 to see what's the limit for that one and what's the limit for shear and bending reduction. So the next is horizontal moment capacity. We have a girder. We had vertical bending. Also, we may have horizontal bending. Just let's say if it is support, and we have this horizontal load, in that case, we will have horizontal bending in that direction. In this case, we are just going to check this horizontal bending by top flange. Top flange can be just one plate or just combined PFC or just combined top plate. In that case, we just applying those MY to this section to check for that. It's the same rules. We need to apply that one, and it should be just applied M should be less than the capacity of top plate in bending. Now, if it is safe, it's okay. If it's not, we need to have just higher section for whole area, or we need to strengthen the top flange. Next one is lateral torsional buckling. We assume that there's no lateral supports on the rail and between supports, and we need to check for this one. So we assume that is unrestrained and there is no lateral support for top flange and bottom flange in general. And so the next is just due to interaction between crane wheels and crane rails, crane loads need not to be treated as destabilizing, assuming that the rails are not mounted on resilient pads. And also, no account should be taken of the effect of the moment gradient, MLT, or lateral torsional buckling factor, should be taken as 1. So for that things, we have just major effect should be less than MB, and MB is the, for buckling we check here, MB should be equal to PBSX, and SX that is just section modulus, and PB is the bending strength and is dependent on the design strength PY, that is yield stress here, and equivalent slenderness lambda LT, that's calculating from this equation BS 5950 4367. If the section is compound, roller section plus plate or just plus PFC, we can use just equivalent lambda LT for this equation. Anyway, it is just easy calculation for lateral torsional buckling for the section due to applied bending. Next one is the combined action of vertical and horizontal bending for the section. We have MX, we have MY. It is easy. We have applied M, design M, or capacity. It is always reduced capacity. And this one is applied M on minor direction and reduced capacity on minor direction. And remember, for lateral direction, we always use just top flange. So this is bending in major direction. And for top flange, we have just top flange for MY. So MY, MCY, it is just applicable for top flange. And if the combination effect is less than 1, it means that the design is safe. Otherwise, we need to increase the section totally or just whatever we need to reach to this factor. And for buckling capacity for simplified method, we use this equation mx/ms, py/zx, py/zy, my py. And this that we talked in previous slide for mlt, m capital MT on MB, MY, PY, ZY. Just we assume that these are the maximum and the minor one is just plate. MLT is the maximum major axis moment in a segment, and MX, MY factors can be taken as 1 for simplicity. These parameters, for simplicity, we can assume that is the all 1 and we can have easy calculation. Another check for web is shear at support. You know that here for I sections in steel structure, we assume that all shear is going to be taken by web. And the flanges are not taking any shear force for this one. So same concept here. If PV, let's say PV is the capacity and V star is the load, or let's say here is just FV. If FV is applied shear on the web, it is just the maximum one. It should be just very close to the support points. So FV is applied design shear should be less than the capacity shear. And capacity shear is 0.6 PYAV. AV is the web shear, web area, that is thickness of web times depth of the section. And we have 40% reduction or 60% of the capacity we're using in shear. That is very common in all design. Another check is web bearing and buckling under the wheel support. We have sometimes big loads under the web, under the wheels, and it may cause buckling and bearing problem to the web. So we're going to check. First, we need to check the bearing area of the web. It is calculating from this equation B1 NK TPYW or the PY web. It is just yield strength, and N is 5 for interior supports and is for end member. It is just N plus 2, N is 2 plus 0.6 BE on K and should be always less than 5. We're using this equation for bearing capacity of the web under wheel. And K is calculating from this equation. If it is just hot roll section, K is T plus R, and T is the area of, flange. Yeah, it's a thickness of flange. And if it is just welded section or cold rod or any welded section, K is equal to T. And R here is just given as this radius. It is very common in just, you know, that what is in hot rolled section. And for buckling resistance of the unstiffened web, we're using this equation. Fx should be less than Px, and Px should be 25 epsilon T B1 NK D. D is the depth of the web, and Pw is the bearing capacity that we calculated here, and T is the web thickness here. We have all these parameters shown here clearly, so we can use those things for checking. And the last one is load compression under wheels. We had bearing capacity, and also we need to check for local compression under the wheels for the web. So we need to have this pressure, applied pressure on the web, less than the yield stress. So we need to check what is the applying or the effective length under the wheel. So if we have two wheels in distance of SW, the applied length should be 2HR plus T. HR is the depth of the rail here, and T is total plate and flange. If we have plate on top of the flange, or otherwise it should be just one flange. So anyway, in general, HR plus these 2T, plate and top flange, should be plus HR multiplied by 2, should be the area or effective area for compression, local compression. But anyway, this area should be less than SW. SW is the center to center of the wheels. And we need to check this equation. And after all, W prime W on XRT, T is the web thickness, is giving FW, and if FW should be less than this PY for web, that is yield strength, yield stress. If it's less, it's okay. Otherwise, we need to strengthen the web or just change the section for higher web capacity. The last point in rail design is deflection check. We have two dimensions for two directions for check. It is major for, let's say, for major direction, that we have this deflection span on over 600 by the applied load, that we just check for the biggest bending capacity here. We already have the maximum vertical load, and we can calculate this delta if we have the girder section. And the second one is in the y direction, that is span over 500. That, remember, this is just for top flange, and we need to check for both criteria for deflection, for serviceability, and if everything is okay, it means that the crane is safe and we can use that girder section for the crane. Otherwise, we need to strengthen or increase the section. And after all, we're going to check for bracket and also for the column to take all these loads. Thank you so much.